our next speaker is Professor Mario Ferrari from University of Genoa. He works on advanced energy system, smart grids, and atmospheric water generation with more than 120 indexed publication and leadership role in European research projects. Today, he will present tests in cyber physical mode for poly-generation grids equipped with AWH and energy storage system. Professor Ferrari, the mic is yours.
Thank you for my introduction. Good morning, good afternoon, or good evening, depending on your time zones. My presentation is about a bit different topic in comparison to what we have seen before. So I'm talking about energy management systems for a polygeneration grid, including atmospheric water generation. In details, I'll show tests in cyber-physical mode performed in our laboratory at the University of Genoa, including energy storage system based on phase change material. So, starting from a motivation, the presentation of the grid with this air water generation system, our atmospheric water generation system. I switch to the presentation of the component models, the energy management system that is proposed in this activity, and the cyber-physical approach that has been used in the laboratory. Finally, the results of a 24-hour simulations based on cyber-physical mode, so it means simulations for the software coupled with real measurements from the hardware, will be presented. So, in general, a polygeneration grid is a very complex object. Just focusing attention on electrical grid and thermal grid, we have different generators, different users. We can have prosumers, we can have electrical storage devices, batteries or other things, also based on power to fuel or something similar. If we have a thermal grid, we can have the same situation. So generators, thermal storage, users, and also systems that are able to generate or use depending on the situations. More complex is if we have not a connection to the external electrical grid, like in an island mode, on an island, or on a system that must be able to be self-sustainable. So, just to focus the attention on the importance of the optimization of these systems is shown here. It is related to a simple test with a T100 machine that is a microturbine able to produce 100 kilowatt electrical power for a 24-hour analysis. So, considering the demand that is shown below in light blue, it is possible to control this machine to follow the demand with this standard approach. It is named as case 1. However, the efficiency of electrical generation is not constant. It's lower at lower loads. Maybe if the T100 machine nominal efficiency is about 30%, at low load could go down to 15%. So, if we have the possibility of storing energy and exploiting this energy when we have excess, or we have missing energy, we can have an approach like this. Machine switched off during the night when we have a low demand condition, and machine at maximum during the day, especially during the central part of the day where we have maximum demand. So, just switching from the case 1 to the case 2 is possible to obtain 17% of cost decrease because of the operation at the highest efficiency when the machine is active. This is a very simple example. You have to imagine that everything is more complex if you have a combination of other form of energy like thermal energy, or if you have water distribution, generation distribution, and so on. So this justifies the need of developing a real-time energy management system for reducing or minimizing costs, or operating on other targets like minimizing the CO2 emissions, optimizing the efficiency, and so on. In this work, I would like to present the grid that has been taken into account. It is based on water grid. Water can be obtained from the aqueduct, or can be obtained from an AVG system, the AVA 250 by GEAS, able to produce both water, clean water, and cooling water for the cooling energies, the cooling demand satisfaction. So we have also the cooling grid. The cooling grid includes for sure the generation from the AVA 250, but also the generation C Gen 2 by the cooling side of a heat pump that is based on butane. It is a heat pump available in our laboratory. It is an 11 kilowatt electrical power heat pump. This is the heat pump is also connected with phase change material storage for the cooling energy. Since this heat pump is able to produce the cooling energy for the cooling side at very low temperature conditions, in our test was down to -6 degrees C. It is possible to use simple water that is converted to ice as a phase changing materials that has been considered here. For sure, the cooling grid is based on connected with these systems here and here with devoted heat exchangers. The cooling grid is including also storage for based on sensible heat that is the largest one that is able to generate good balance between generation and utilization in the grid. The electricity needed for the two electrical components, the AVA 250 and the heat pump, can be obtained mainly by the general electrical grid, but with some support of PV panels that we have available. This is a small system, 1.1 peak kilowatt power, but it's what was available in our laboratory. So the demonstration of the effectiveness of the application of these systems has been already analyzed. For the AVA 250 module, so in the website of the SEAS company, you can see demonstration related to different test cases. One that is reported here has been performed in Dubai. So it has been demonstrated that the payback period could be lower than 2 years if both cooling energy and also heating energy are exploited for specific local needs. For sure, cooling energy for ambient conditioning, and heating energy for hot water for washing, for showers, and something similar. We have taken this machine into account, this machine that is able to produce a maximum amount of water of 2,500 liters per day. Air flow rate that is treated is 1,000 cubic meters per hour with the traditional cooling fluid air 134A. So first of all, we have developed some component models for components not available in the laboratory. The AVA 250, the water storage tank, and the thermal storage tank. They were based on global balances, very simple models, because our analysis is related to the grid interaction, the grid economic balance, not on the specific details or the specific components. So we don't want to know the temperature, pressures between some components of the AVA 250, but the target is the global parameters in terms of cooling power produced, electricity consumed, and so on. So the AVA 250 model has been based on interpolation of performance maps for a steady state part and first order delay blocks for the transient behavior. The validation has been done in comparison with the laboratory inverse cycle that we have, and here you can see a good matching between the calculated results by the model and the experiments. For the water storage tank, it was 2000 liters, and the basis of an integrator that we implemented, we have the calculation of the state of charge from the inlet-outlet balance. Then for the thermal storage tank, the same for the hot water for the cooling side, for 2000 kilowatt hour in this case. Here on the right side of the slide, you can see a comparison of the model results with the experimental data. For sure, it's not possible to check to recalculate the specific oscillating behavior that we have at the beginning of the startup. However, we have set correctly the delay components to have the correct calculation of the generic transient trend that is very important for what you like to do. The system includes also PV panels. It is a generation between 9 to 16 hours of the day. Measurements have been obtained during a low irradiation month. It was February, so maximum generation was about 650 watt in the middle of the day. Then we developed also two models for the components that are real hardware in our analysis, because they are used for comparison at the end of this presentation. So this is the R600 heat pump that has been developed on the basis of the interpolation of performance maps for the steady map part and first order delay blocks for the transient behavior. Thanks to this heat pump, it is a Mayakawa heat pump that we have in our laboratory, we compared, obtaining good matching, our model results with the experimental data that we measured. This for the cooling power. The phase change material-based thermal energy storage tank has been modeled based on inlet-outlet thermal balances, and the size was 100 kilowatt hour, not very large in comparison with the other one, but it is the device available in our laboratory. Also in this case, we compared for a discharge, the startup of a discharge phase, the model results with the experiments obtaining a good matching. The energy management system has been developed in MATLAB Simulink for minimizing the variable costs on the basis of the selection of three decision variables. Here it's possible to see the cost function. The three decision variables are water from the water grid, from the aqueduct, the electrical power of the AVA 250 and the electrical power of the heat pump. It's possible to see that the optimization is not linear, and it is based on constraint approach, because we have some minimum maximum values of constraints, but we have also constraint equations, like the fact that we have to balance to satisfy specific demands of water and cooling energy. Then the water storage tanks has been implemented, so managed on the basis of scheduling. So they can be charged in case electricity cost is lower than the daily average cost, and for the Sensible heat water, we need RWG active. In case of the phase changing material, we need to have the heat pump active because these are the only components that are able to interact with them. The discharging phases are activated in case of electricity costs higher than the daily average. So it is a general approach to consider proficient from a cost reduction point of view, this approach as demonstrated in previous works. Then they are constrained to minimum 10%, maximum 19% of their state of charge values. Since we have developed initially simulations just using models, it was important to switch to some real components, considering what we have available in the laboratory. It is quite hard to have the availability of everything to install a specific devoted smart polygeneration grid, including all the needed components. So, for instance, we don't have in our laboratory an AVA 250, so we have switched to a cyber physical approach. This is also considered a good approach because in case of problems, we have no risks of wrong managing components that are sensible, fragile, dangerous, and so on. So here you can see on the right the laboratory. The laboratory includes the heat pump by Maekawa that has been used for the cooling part. The phase changing material vessel, that is this one, and some resistors here in this tank for generating the load for dissipation, so just for simulating locally thermal demand. On the other side, we have a model. The model includes for sure the energy management system, the MATLAB optimizer, and the logic that has been presented before, and the models of not available component in the field that are the AVA 250, the clean water storage, and chilled water storage. In real-time mode, there is an interface, input-output interface, to be able to perform tests in a so-called cyber-physical mode. So the optimizer calculates the on-off signal for the heat pump and the in-out command, so charging, discharging for the phase changing material tank. So if it is in charging and discharging phase, at which a command of kilowatt power to be exchanged. And these data are the set point, the data calculated by the model in reality, so the signals by the optimizer output, and transferred to the test rig for managing the plant. On the other side, we have measurements like the heat pump power values measured second by second. The phase change material in out power, because one side is the command, the other side is the actual measurements. And the phase change material state of charge. We have a state of charge measurement on the basis of pressure variation that is significant for giving us a state of charge signal for the state of charge of this system. So here it's possible to see the results. We have analyzed 1 day, 24-hour case with ambient temperature and ambient humidity reported here. It is representative of a summer condition with a lot of humidity, especially during the evening. Then on the right, we have a double peak trend of electricity costs with a peak in the beginning of the day and during the during the evening. These are the cost data for the water, 2 euro per megawatt hour constant for the entire 24 hours, cooling energy 45 euro per megawatt hour, and operating maintenance costs 10 euro per megawatt hour for both the AVA 250 and the heat pump. On the bottom, it's possible to see some results. So the results obtained with the EMS, the Energy Management System, have been compared with a reference case, a no EMS case. The no EMS case has been developed considering a simple management without any intelligence, just for following the demand. Maybe with the AVA 250 when it's possible, switching on the heat pump or when the cooling demand was being higher, switching off and something similar. So it's possible to see that in the initial 4 hours of the day, the EMS maintain off the AVA 250 because not proficient. Mainly due to the fact that we are during the night, the humidity is about low, and maybe it was considered fruitful to obtain this water from the aqueduct. Then in the second part of the morning, between 4 to about 8 a.m., we have a strong utilization of the storage systems because we are in a high cost of electricity, and so software decided, the DMS decided to use for the possible amount the water and the cooling power stored in the storage systems. Then after 8 o'clock, we have the activation of the AVA 250 because we have an higher temperature, higher humidity, and it is effective for producing a lot of water. Then we have a sort of a continuation of the day. At about 11 o'clock, we have a peak in the demand of cooling, so the AVA 250 was not enough, and the heat pump has been activated. Then it's possible to see then the heat pump then has been deactivated, and finally we have also the activation of the AVA 250 when the demand of cooling and also for water started to be so low, like after 20 p.m. 20 so 8 p.m. In the final part of the day, we have again some utilization of the storage, and then finally no further activation of the AVA 250 because not considered useful. Here we have a slide about the storage systems. It's possible to see when we have the peak of electricity costs, we have the utilization here and here and here and here for both the water storage and the thermal storage for the one for the cooling energy. For the phase change material storage, we have the same here utilization here and here. However, we have a significant decrease of the state of charge due to the heat loss because the circuit maintained the pumps active, and we had about 1 kilowatt enough of discharging due to not perfect thermal losses. This generated a lot of decrease in comparison with the no MS case, and so the state of charge has been decreased lower than 10%. For this reason, the heat pump has been maintained active for more time for recharging the system. Here you can see a sort of comparison between simulations and cyber physical tests. So while in simulations, when everything was not active, the state of charge had been maintained constant because just simulated with no specific real data about this. For the real case, with including the real component in a cyber physical approach, it's possible to say that due to this big decrease of the state of charge, here you can see the heat pump has been maintained active for 2 hours more or less for recharging the storage as necessary. So in conclusion, I've shown the importance of DMS technology in smart grid, the development and validation of component models, the development of DMS for variable cost minimization, and the results in this 24-hour test has shown a significant cost decrease that was minus 20% in the case of simulations. However, in the cyber physical approach, using real components for the heat pump and the phase-changing material-based tank, it was possible to say that the variable cost decrease was lower, however significant, because minus 16.4% is anyway significant just for one day. So if this is multiplied by for a lot of months, for sure the advantage is important. So that's all. Thank you for your time, and I'm available for questions.
Thank you, Professor Mario. That was very interesting, especially the very clear cost analysis during time frame. Thank you, Professor.
Thank you.
We are going for our next speaker, Mr. Joab Kirsch, the co-founder and CEO of H2O. He develops commercial AWS systems using innovative absorption technologies with deployments across the US, Mexico, India, and Middle East and Africa. His talk is titled The Absorption Revolution, H2O, Drink Water in Dry Zone. Please go ahead.
Thank you very much, Amin, and I'm very excited to be here today and participate in this unique session. I think we all know that the atmosphere contains a lot of water. That's why we are all here today. And we also know that the main challenge is that the concentration of water in the atmosphere is very low. And there is a big challenge to extract the maybe 2% water vapor that we have in each cubic meter of air. And actually what H2O did, our inventors, which are professors from the Technion, were able to find this new technology based on absorbing the water that can produce the water not in 2%, but in 100% water vapor environment. And this is a very big message to the world of atmospheric water harvesting. And I'll of course present this in a bit. My name is Joab Kirsch, as you said. I'm co-founder of H2O, and I'm all in this wonderful venture. And I would like to start by sharing a short video, and then I will proceed to explain what we do and how we do it. And we do say that we provide drinking water in dry areas. This is what we feel is our mission and vision. This is what we do. So I'll go to the next slide.
The problem of water in the world is a pressing problem, and we're going to live with water scarcity.
We are running out of water. Double the amount of all the freshwater reservoirs in the world. We at H2O produce water out of the atmosphere. H2O actually brings life through its water. More than 1.1 billion people around the world are in critical water shortage, and a third of them live in dry inland areas. We are aiming at these 400 million people to help them have water in a way that's sustainable, affordable, practical, and very efficient. We produce water out of air. There's the atmosphere, we take the air, we run it through liquid salt, and we create water.
Most of the technologies that are available in the market today are based on direct cooling. This is problematic when the concentration of water vapor is low. Our system is a two-cycle system. In the absorption cycle, we absorb the water through the desiccant, and in the second cycle, we release the water vapor back into a confined atmosphere. And that's why we can be more efficient than other technologies. What we do is for the benefit of humankind.
We're driven by a shared passion to address one of the most pressing challenges facing the future of humanity, ensuring access to safe drinking water everywhere and at all times for everyone.
The problem of
So I hope you heard it was audible. Great. So we all know these numbers, and this is an opportunity to share my initial experience of thirst, which occurred when I was 17 years old, and we were actually trekking in the Negev desert in the southern part of Israel. It was a 4-day trek, and we could not carry all the water on our backpacks. So the whole trek was planned according to where will we find potentially water. And even when we did find water, it was usually a very low current stream, and it took a lot of time to fill the water, while just above us lay the atmosphere, and we all know that the atmosphere contains a lot of water. So actually, what the H2O has developed, and first of all, when I experienced the thirst, now I understand, and we all understand, that it's not just my or our specific problem, that a lot of people around the world are thirsty, and one of the problems is that the ground resources are becoming obsolete or depleted, and the atmosphere is a new source. I have to say that what Paul said in the beginning was very inspiring, and I think that atmospheric water harvesting is on the verge of erupting and becoming a very prominent player, and to follow suit with the PV developments. And actually, as I said before, the technology that we developed allows us to work in specific, very low humidity conditions. Namely, we can work as low as 5 grams of water vapor per 1 kilogram of air, absolute humidity. And you can see this on the blue area that is on this slide, compared to legacy technology of direct cooling, which needs at least 10 or 12 grams of water vapor per 1 kilogram of air. So this is, of course, a schematic slide, but our zone of activity is a lot wider than the existing technology, and we can work at half the absolute humidity, as I said. And since the topic of this specific webinar is Africa, Middle East, UK and EU, you can see that we can work in many areas that the current technology would not give a good solution. So it's North Africa, it's EU, the Middle East, Southeast Asia, Australia, and of course North America. So how does it work, and what was actually developed in the Technion? So we have an atmospheric water generation technology based on absorption, and it's a 2-step absorption technology. In the first step, the air through a blower is drawn into an absorption tower. In this absorption tower, the air is run through the liquid desiccant or brine. It's a salt-based desiccant, and the desiccant actually absorbs water vapor. As we all know, this is an almost passive process without using any energy. And then we heat this liquid, which is very rich with water vapor now, and we transfer it into a production generator. Now, in this generator, with heat and deep vacuum conditions, we desorb the water vapor from the desiccant. The desiccant goes back in a closed circuit to the absorption tower. And now within the generator, we have 100% water vapor conditions. And only then do we condense the water and produce high quality distilled water. The only thing left to do is to remineralize the water for health, taste, and standard purposes. So this is the big message that we bring to the world of atmospheric water harvesting. 100% water vapor environment when you produce the water, compared to legacy technologies that work at 2% water vapor environment. There are additional upsides to this technology. Apart from the ability to work at half the absolute humidity, we are working at half the energy compared to legacy technology, and we also offer a stable consumption of energy within the operating conditions. So regardless of the weather and the humidity, we will consume the same amount of energy, because when we produce the water, there is always roughly 100% water vapor environment within the production generator. One more big upside is that the liquid desiccant is actually a natural filter. We don't need artificial filtration. because the liquid desiccant actually blocks any type of contamination. No PFAS, no germs, bacteria, physical contaminations, or air pollution can pass. We have a commercial system which is deployed today in the Negev desert in Israel, in a location which has a lot of dust storms, and the water coming out of the system is still pure, potable, high quality water. I would like to show, a graphic presentation of the comparison between the direct cooling and our absorption technology. Our technology is in the blue graphs and direct cooling is the green graphs. And even if you're looking at associatively, you can see a very prominent, picture. The blue graphs are a lot more stable than the green graphs. And this is actually one of our main upsides. We offer a stable production of water in all the weather conditions that we operate in, and it's a very wide area, as you saw before. And we offer also a stable energy consumption. So if you look at the dotted green compared to the dotted blue, the dotted lines are the energy consumption. You can see that the dotted blue is a lot lower than the dotted green, especially in the dry areas. Same goes for the water, which is a lot higher. So we can produce a lot higher quantities of water at a substantially higher SLA compared to the green direct cooling line, again, in dry areas. That's why I said before that the message we bring to the world is that we can produce high quality drinking water in dry areas. How we do it? Of course, by harvesting water from the atmosphere. This is the system that is a commercial system, which I said before, it was developed at the Technion in the Civil and Environmental Department, Civil Engineering Environmental Department. We have 2 granted patents in the United States. This is a 1,000 liter per day system working for more than a year now and producing water to a Bedouin school in the Negev region of Israel. 1,000 liter, we all know the World Health Organization standards, so it's sufficient for 400 people. And you see here, this is a very moving picture for me to see the children of the school on a daily basis going through the system and drinking this fresh water, and they are very excited about playing with this faucet that we have there. For us, it's really a very moving scene, and this happens on a daily basis, as I said. And now you can imagine this system, which is an off-grid system, deployed in a new residential project in a dry inland, far away from the sea, city. It can be in Spain, it can be Tamale in Ghana, it can be in the Middle East or in any other dry location around the world. You bring the system, you plug it to a sustainable source like PV, wind, or any other source. And of course, you can plug it to classic sources like the grid. And in a matter of a few hours, you have a reliable, high-quality source of flowing water. As we all know, the atmosphere is not depleted. It was also mentioned in previous presentations. There is a lot of water, and we are not drying up the atmosphere. So I would say this because it was asked before by many people. I mentioned before, we're working at half the humidity and energy, and the quality of water coming out of this system is top quality. It was checked by the Israel Ministry of Health laboratories, and we are compliant with a wide spectrum of international drinking water standards, such as the WHO, EU, the Israeli standards, which is very strict, US bottled water standards, and a lot of other standards. We are asking ourselves, what are people doing today? Of course, I'm speaking to people who are experts in water. And to meet this challenge of 24/7 drinking water in dry areas, our system is able to do that as an atmospheric water harvesting system. We know that legacy systems are challenged in dry areas, and in many instances, they cannot provide water at all. And the existing sources in 2025, still, it may be even outrageously said, are mobilizing the water by trucks, or existing sources of drinking water in dry areas today are mainly trucked water or bottled water. These are two unenvironmental solutions. They are unsustainable. They are usually very expensive, while we can still provide as us as H2O and also I'm sure other solutions of water generation, a high quality, reliable source of water, which is a lot more environmental and carbon friendly than these two existing solutions. So talking about SDGs, it was discussed before. I'm moving to the next slide. You know, water is actually linked to 15 out of the 17 United Nations SDGs. Because poverty, hunger, well-being, education, gender equality, and other standards are all linked to water. So we are providing a very important solution to many of the SDGs. We are offering our clients two business models. We can sell the water or sell, of course, the systems. And actually, one of our prospective clients offered the third model, which is, why don't you give us a lower price for the system and we will still pay something for the water. So this is the third model that we are using. And I think, again, referring to Paul's example of PV, the market needs to still understand atmospheric water generation, and we have to be attentive to what the market needs so that we can indeed make this leap up of the whole market soon enough, and I think it is going to become soon. This is what my feeling is. Going to the next issue, which is milestones and traction. The company is actually, as I said before, has deployed the commercial system of 1,000 liters per day at a school in the Negev Desert. This was a joint project with the Israel Innovation Authority, and we actually received 75% funding for this project, and the matching was done by us, the founders of the company. And we are thinking of now under planning is the next generation 10,000 liter per day system. And after successful implementation of this system, we will also go into the planning of the 100,000 liters per day. So I hope we will contribute to the target that Paul said before of 1 billion cubic meters per year in the best way that we can. We also are now in key markets. We have MOUs and LOIs, and our markets are from Southwest US through Mexico, the Middle East, Africa, and Asia, specifically India and Indonesia. We concluded a $2 million crowdfunding last year, and we're winners of some accelerators. Maybe people are acquainted with Mass Challenge and of course Polaroid Science, which is a very well-known company in the United States. There are many applications. We all know that, and I'll just tap quickly that in the go-to-market stage, we feel that private sector is more resourceful and quick, so it's more suitable for the penetration stage. And we are talking now to clients with different progressive stages, but some of them are very progressive, from the industry looking for water for employees in the chip, in the data center, and in the PV power parks industries. Hotels and resorts are, of course, a natural client, especially in dry areas, and the real estate market. But this is penetration stage. The growth and value lies with governments and municipalities, where you have a lot of applications that you can see listed here. And specifically, we are now talking to emergency agencies to implement our solutions. This is our team. It's a very experienced team from the business and technical point of view. Mr. Ilan Katz, our CTO, who is the person who built our first POC some 5 years ago in the Technion. This POC is producing for the last 5 years 200 liters per day in various weather conditions and various pollution conditions, because it's just above the Haifa Bay, which has heavy industries, and some of them are quite polluting, and still the quality of water is very high. Mr. Leonardo Polinsky, our VP Sales and Business with substantial go-to-market experience, and the scientific committee, which is leading professors from the Technion. I assume some of you know some of them. Professor David Brodai, who is atmospheric science expert. Professor Friedler, who is head of the Grand Water Institute in the Technion. Dr. Khaled Gomed, who is an expert in absorption systems, and Ben Guido, which is a wash expert. So I thank you for listening, and if there are any questions, I'll be very happy to answer.
If there is any question, please just raise your hand. I will unmute you. But anyway, in the meantime, you received some question in the chat. Have you ever tested the ammonium concentration in the harvested water?
What I can say, I don't remember specifically about ammonium, but we have tested more than 200 elements in the water. The tests we are running are very, very thorough. And the water were found, as I said, to comply with all the leading drinking water standards. As I mentioned before, the US bottled water standards, the EU water standard, World Health Organization standards. So I think that if it's important to hear the specific issue of ammonium, I'll refer to it separately, and I will check it in the test, and I can back to you, Roberto, if you can just put your email here.
Okay. Ibrahim, you are allowed to
There is a
unmute.
there,
Yeah, to unmute. Yeah, later we will come back to the chat. Ibrahim, you can just unmute yourself and just ask your question.
Yeah, I can see a very interesting energy consumption for your system, but I'm wondering about the regeneration temperature you need in your system. What is the minimum temperature you need in your system? Thank you.
the minimum operating temperature is 5 degrees, and the maximum is 50 degrees.
I mean the minimum temperature for regeneration, for desorption.
For the regeneration, sorry. This is 50 Celsius. We regenerate in 50 Celsius, and as I said, in deep vacuum conditions as well.
Thank you.
Okay. Going back to the chat, here's Anton from Qatar University. I would like to ask what the approximately price is for 1 liter of harvested water.
Yeah, so 1 liter of water in our system, and this is an all-inclusive price, is 12 cents per liter. Out of this 12 cents, 8 cents is energy. So if we take the energy off, we are at 4 cents, and I'm not taking the energy off because there is no cost of energy, but because energy prices varies, and some of our clients, they have a lot of energy, sometimes surplus energy. So they will face 4 cents per liter, which is a very, very competitive price for this type of drinking water. Again, when the alternatives are trucked water and bottled water. And the OPEX cost, there is a question about the OPEX cost. So as I said before, OPEX is mainly energy. Maintenance is very low. It's around 1 to 1.5 cents per liter. So the 12 cents are 8 cents energy, 1.5 cent operation and maintenance, and 2.5 cents capex. Again, capex can vary because it depends how much capex. So, but this is the breakdown roughly.
Thank you. And Nancy asked, what is the estimated lifespan of your system, maintenance cost?
Yes, the system is mainly comprised of generic pumps and heat exchangers, and of course our patented condenser desorption and the absorption tower. We assess at least 10 years of operation, but probably it will be longer. We can see 15 years as well. So it's a long-term system. It's like an industrial system.
Thank you. Ibrahim, do you have any question? You can just unmute yourself.
Yeah, sorry for asking again. Regarding the liquid desiccant material that you used, what is this material? Is it like conventional material, or you guys develop a new material in your system?
Now we're using lithium chloride.
Thank you.
Also present here is Ilan Katz, our CTO and founder, so he's also answering in the chat. So we see there is no ammonia, so this was referred to before, so you can see the answer now.
Awesome. Any more question? If there is any more question, just write in the chat or just raise your hand.
I think there is a question about the energy consumption, if I
Yeah, please
understand
feel free.
correctly.
Yeah, please feel free to answer.
Yeah, so this would be between 0.5 to 0.7 kilowatt hour per liter, and on average it would be 0.6. Again, this is a reasonable energy consumption, and we are working on the next generation system of 10,000 liters to make this a lot better, alongside with better water efficiency, although we are also happy with the current production of the systems.
Okay, awesome. Thank you very much.
Thank you. It was a pleasure, Min.
Thank you. And our final speaker for today is Dr. Daniel Salcedo Serrano, research scientist at Arizona State University. His work focuses on benchmarking energy efficiency, water purity, and performance of desiccant-based and condensation-based AWS systems. He will present from air to water benchmarking energy efficiency and water purity in AWS systems. Dr. Serrano, go ahead, please.
Thank you, Amin. I'm gonna share my screen. Yeah, so thanks for inviting me. It's the last presentation, so I'll try to make it brief, try to entertain you somehow. I'm gonna talk about a fun and very insightful experiment that we're doing here at Arizona State University in Arizona, southwest of United States, and it's benchmarking energy efficiency and water purity, sorption-based versus dew point condenser-based atmospheric water systems. So a little bit about what this project is. There you go. Well, it's a 1 year long ongoing study where we compared two types of systems. One is the dew point condensation against the sorption-based humidifier systems. But this is all done in the outdoor setting. And we monitor continuously the water production, the energy consumption, and the environmental conditions in order to compare vastly the energy intensity for water production and the water quality, which is, I think, something that might be interesting. I think we feel that this type of works, although small, they're really important when you're dealing with developing new strategies, which brings me to this next point, which is all of this is with the scope of looking for freshwater supply strategies in arid regions, as I think most of us are. And this project is part of a greater effort that is called Arizona Water Innovation Initiative. The main project, and beneath that there's Arizona Water for All, and it has one of several missions it has is to create modular, adaptive, and deployable solutions to target water insecurity in rural, underserved communities. Okay. All right. So for this comparison, we use one dew point condensation unit and 3 sorption-based humidifier systems. Again, this is for testing the amount of water per energy and the water quality, rather than using a brand specific benchmarking. We're more interested in the outcomes to interpret this for freshwater supply alternatives. So this is how the setting looks. So we have the dew point condensation unit, and this is a 50 pine Evasion. It's the brand compressor-based condensation unit. So what it does is it has like this aluminum coil that cools down the air, and the water trickles down to it. it has an airflow. The system sucks in around 367 cubic meters of air per hour, and this is important, but I'll elaborate later. And then we have what we call the DR units, which are the CLA porous absorbent rotating wheel designed from Evasion. They're dehumidifiers, and it's the same brand, and they suck air, uh, the air that the airflow that they work with is 84.6 cubic meters per hour. Now, what we call the CR and the DR1, they are installed in the roof of a building that we call the ERC. It's about 30 meters from the ground level. And the other two sorbent-based units are installed out in about 15 meters high above ground in different locations, a balcony, and it's 350 meters away approximately from the other units. They are out in the open. They have this cover, but they're basically out in the open. They're not exposed directly. They have a small cover, and this is actually a picture of how it looks in front of the ERC setting. So you can see it's like pretty much exposed. Okay, so this is the flow diagram. This is the installation setup. It might look overwhelming, but it's quite simple. So in this, we're going to use as an example the ERC setting. So A is the dew point condenser based unit. B is the sorption based dehumidifier system. So we have a logger where we register the relative humidity and temperature every 10 minutes. Then we have a water production logger, so which is here, but it connects to the bucket, the letter E. So every time there's some water produced, there's a tilting cup, and that tilting cup sends a signal, and that tilting cup is equivalent to 8.6 millimeters. That sends a signal to the logger. And then F is just the acrylic bucket where we collect the water as a reservoir. And the G right here is energy consumption meter. So the flow goes like this. Either A or B are working. They're constantly being monitored. They're sucking each one different quantities of air or processing different quantities of air. The water is produced, so it sends a signal. It sends a signal to the logger, and this production is related to an environmental condition, and then it just trickles down to a reservoir, and we collect the water from there. We collect the data every 7 days, so it's Monday to Monday. Okay. And the water analysis, what analysis do we do? So we do the general testing, pH, turbidity, electroconductivity, also total organic carbon. We test for what we believe major anions and cations. We also test for microorganisms, specifically for total coliforms, E. coli, and Pseudomonas aeruginosa, which is for us an indicator of bacterial activity and biofilm formation. And we also test a lot of like metals and metalloids or elements. We use suite 71 A and B from Inorganic Ventures. If you know those, but it's basically 71 elements that we test. So let's go straight to the results. Well, this is the graphic that we got from. Oh, I forgot to say we're gonna show the first 17 weeks of the project. The project started on March this year, and for this presentation we cut at July. 14. So this is the trend of the relative humidity at the atmospheric conditions. Is a result of 20,052 data points, because every 10 minutes we're taking the data. It's 10 minutes interval, and we're using 3 different loggers. So it's 2 on the ERC and 1 at the balcony. And I mean, there's a trend that you can see, like the average relative humidity is usually below 40. It's more between the 20s and 30s. There's maximums, yeah, as always. There's like small maximums, but the average stays here below. I think this is important for next results. Okay. So what we did also is that with the amount of water that was being produced every 7 days and the amount of energy that was being consumed every 7 days, we did a graphic where we try to see the unit's performance in liters per kilowatt. So as you can see, the compressor-based, the dew point condensation unit didn't do well for the longest time. It was really expensive to keep it running, and the production was really low up until the end. And if you're familiar with Arizona or this part of the desert area, there's a phenomenon called monsoon. There's a monsoon season, and all of a sudden the humidity spikes up. But most of the time, due to the low relative humidity, the liters per kilowatt were quite low, and the absorption-based units kept kind of constant, kind of low. I mean, low fluctuations. Okay, we did something else. We tried to estimate the efficiency. So what we did for that is there's a theoretical value, which is called absolute humidity, of the amount of water that is available in the air in grams per cubic meter of air. So given the known air draw that each unit had, we calculated a theoretical amount of water that should have passed through the unit. And then we compared that theoretical amount of water with the actual water that was actually captured by the unit. And that gave us the water capture efficiency. And we have a nice summary here of the 17 weeks. So during these 17 weeks, the CR unit, which is again the dew point condensation unit, consumed 1,992 kilowatts hour. The mean consumption during that period was 596. Through that whole period, it produced 477 liters, but the water capture efficiency was only 4.1%. And the energy to water, so if you just divide the amount of kilowatts consumed and the water that was produced, you get kilowatt per hour per liter, kilowatt hour per liter. And we got 4.2. On the other side, the sorbent-based units, they did consume way less energy, but that's, just because of the system. But that's what we like about the water capture efficiency and the energy to water. Regardless of the type of system or the size, we can compare those with these units. So the sorbent base was far more efficient, capturing the water that was theoretically available in the air, and the energy to water was similar. If we add the 3 units, the triplicates, if we add the consumption of the 3 units, it's still comparable to efficiency and also to the energy to water, which I think it was really interesting. And this comes because the compressor would only work when the relative humidity was higher than 30%. And if you remember on the last graphic, that was not the case most of the time. And the sorbent-based units will work or will capture water in low humidity as low as 18%. I think that's one key thing. Now let's go to water quality. So most of these are related to the type of system and how do they work. For example, the turbidity, the compressor-based unit, the dew point condensation-based unit has a big aluminum coil exposed, and that's where the hot air gets, the water gets captured and condensed. So that means that it's exposed to a bunch of other things, given that it's in an outdoor setting. So the turbidity was way higher. It captured more organic carbon. And also, when there was air, it apparently it also captures salts that were carried out by the air, and of course, they would capture gases, and some of them were considered acid gases, which we'll see later. And you can see the pH with the dew point condensation system. The pH was always lower, was below, well, only on the last one not, but they were usually below 7. Not the case with the sorbent based. So on ions, we can see again this scavenging of particles that the CR unit had. And so we see higher of those. While they're quite not much, I mean, very small amounts. There was some. It's just curious to see some degree of salts driven from the air at that height, but here they are. And also quite interesting is nitrites and nitrates, which either were captured as so or were eventually transformed due to bacterial activity during the week of water being held in those buckets. Someone asked for ammonium. We can see ammonium here. Again, the CR unit had the highest. So yeah, so what are the practical implications for this? Well, the CR unit, the CR system would require higher post-treatment to meet potable standards, whereas the DR systems offer water quality advantage, which is translated, as you know, in energy and cost. So from all the metals and metalloids that we tested, we could see clear contamination, we feel, from the unit itself, because, for example, we saw high aluminum, well, high, not that high, but presence of aluminum in the CR system, which has aluminum coil or aluminum panel. Kind of makes sense, and more if you're dealing with low TDS and slightly acidic water. There's a slight corrosion there. And also we saw very particular for the desiccant based ones or the sorbent based ones, some degree of tin. So we also assume that that's due to the presence of some connections or piping from the insides of the unit. And I think this is rather than just fixating on the metals that we found, it's something important to consider that there will be some leaching from the materials that we're using, which is something to consider. Okay, so from the microbial indicators, there was pseudomonas aeruginosa on all of the systems, but the highest presence was, of course, again with the CR, which is more exposed, and we can kind of explain their prevalence and how they did so well in the water if we take into consideration that we found some nitrates there, which they are fond of, and there's some total organic carbon dissolved there, which is their carbon source. So bacteria could be doing fine in that media. No E. coli, which is good. Even though the winds can blow pretty much anything, there was no E. coli. But there were some coliforms, which is an indicator again from some degree of dust capture. So in the practical sense, both systems would require either UV or an oxidation treatment. After these 17 weeks that I mentioned, we can make like a partial conclusion. So what we know is that water quality is good. It's and this ion concentration is it's orders of magnitude lower than tap waters. It has some issues with bacteria, but they can be treated at low cost, which translates in low energy requirements also. The energy efficiency was comparable in both systems. The energy intensity, though, on the other hand, is, I mean, this data is not to say that we're going to use these units to be deployed and get water to people. If you think about doing that, it will be 1,000 times higher the cost than the commercial desalination energy cost that's already out there. But again, I think these results provide supplemental some sort of evidence on where to look for or what direction to take if you're trying to do this in a bigger scale. Well, again, these results emphasize that while atmospheric water harvesting can provide supplemental water source in the desert, large-scale deployments require significant efficiency improvements, of course. And by quantifying real world performance under extreme desert conditions, we think that this work provides a benchmark for designing the next generation of atmospheric water harvesting devices as a supplemental to move from supplemental to dependable water supply. I just, as an acknowledgement, this work is supported by the Global Center for Water Technology as part of the Arizona Water Innovation Initiative's pilot infrastructure evaluation testbed programs. Special thanks to Dr. Paul Westerhoff, Amin, Mojidi, Chawasia, Hanfu, and Lee Botgader. I'll take questions now.
Please, any question, please just raise your hand. I will unmute you, or you can just ask in the chat. What are the applied post-treatment methods for harvested water? Anton asked in the chat.
What are the applied post-treatment methods for harvested water? Right now, there's none, but I would suggest, I mean, as if we want to go as cheap as we can, I would suggest just using UV or any oxidation with like chlorine, something cheap. We're not applying any now, but that would be my go-to.
And there is one more question from Dr. Lucia. Did all systems display ammonia concentration? And how was the air filtration section?
Yeah, there's some ammonia concentration in all of them. But it was way higher on the CR, but there was ammonium in all of them, yes, at some point, not all the time.
Okay, any more question? You can just raise your hand or just ask in the chat. Okay. Yeah, Dr. Lucia asked. Yeah, I guess Dr. Lucia, unmute yourself.
Thank you. I have another curiosity. Were all the systems built with parts that were supposed to come into contact with condensate were built in certified materials for food and beverage contact? Because the turbidity that I saw was something unexpected, and also the meters that we saw inside maybe was released by the parts of by the components of these systems.
Yes, that is expected. That was expected. So these units are not built. They're dehumidifiers, and these are not built for human consumption. What we were testing was the capacity of the technology to produce, to capture the water, the energy, and the water quality as it is. I don't think the equipments were built for in food grade level.
Okay.
Definitely, yeah. Some modifications should be added if we were to design a system using this technology, for sure.
Thank you.
Thank you. Any more question? If not, we are going to announce the best presentation award. Any more question? Okay. Mid of January, we will have International Atmospheric Water Harvesting Summit at Arizona State University. And today we have two best presentation award. One for Dr. Mohammad Ahmed Jamil. Are you here? Okay, let me unmute you. Yes.
Hello. Yes,
Yes.
I'm here. Thank you very much. Yes.
So you will receive registration waive and also the hotel at Phoenix area for our summit, January 15 and 16. And you will receive one certificate. Is there any point you want to share with our attendees here?
Yeah, I would just like to thank the whole organization committee and particularly yourself because you have put a lot of efforts in managing all the things. So it was really great experience in presenting developments in the field and listening from all other experts. Thank you.
Thank you. So see you during January here. And next presentation award going for Professor Hafiz Muhammad Ali. Are you here? Yes, please unmute yourself.
Oh, yes, I'm here. Thank you very much. I really appreciate that. And this is excellent. Thank you.
Thank you. You will receive registration waive, and I hope we can see you during January at Arizona State University, and you will receive one certificate. Thank you.
Thank you.
Thank you. If you have any point to share with people, please feel free to share.
I think that this webinar and altogether, the thing this like association is doing, this is all great. And just keep doing. And I think it is a great platform, just to share the new work and ideas. And that's it. Thank you very much once again. And this was a nice webinar. Hopefully to see you in coming January in Arizona. Thank you.
Sure. And right now, people, everyone unmute yourself and please open your camera. We want to have a selfie, e-selfie. Everyone, even people who just join us, you can just unmute and yes. So I hope more people join us. Just unmute yourself, open your camera, we can see you and take a selfie. Thank you. More people, I hope more people join us. Okay, thank you all. You can just say cheese. Okay, I really appreciate all and see you next time. Thank you. Have a great day.
Thank you. Bye-bye.
Thank you.
Thank you.
Bye-bye.